So last class we left off right about here, speaking about what happens at the end of the action potential, and we got to speaking about hyperpolarization. And hyperpolarization is really that ending off or that tapering off of the action potential where we have completely repolarized the membrane and we actually overshoot the membrane potential. What does that mean? That means that instead of going just back to -70, which is your resting membrane potential, we go a little bit further negative and we get to about -85 millivolts. So we go further negative than rest. And this happens because there are still some of the voltage-gated potassium channels open, and so we polarize that membrane excessively. Then at this point, at about -85 millivolts, the sodium-potassium pumps kick in and they reestablish the potential at -70 millivolts, which is your resting membrane potential. Okay, so that overshoot is sort of a reflex in the drop of the membrane potential caused by the opening of those potassium channels, those voltage-gated potassium channels. Okay, and then we get right back to our resting potential, which is -70 millivolts, and from here on, we can generate another action potential. During this period, it's going to be a little bit more difficult, and we'll talk about what that means. Okay. So now we understand the mechanics of an action potential, the channels and the movement of ions. We're going to speak about some of the properties of an action potential. First of all, there's the all or none principle. And this means that an action potential has a threshold, and above that, it's all or nothing. Okay, all or nothing. Once we get to that threshold, we're going to fire an action potential. If we do not get to that threshold, we will not fire an action. So it's the minimum depolarization that's necessary to induce the regenerative mechanism for the opening of these sodium channels. So these channels open at -55 millivolts. That is all or nothing. Okay? If you don't get to -55, these sodium channels do not open. If we get to 55, if we get to 56, 57, the channels will open with the same amplitude, the same duration, okay? And in this regard, we have three types of stimuli. We have a threshold stimuli, which is going to generate an action potential. We have a sub-threshold stimulus, which generates no action potential. And then we have a supra-threshold stimulus, which although it's a stronger stimulus, it's going to have the same type of action potential. There's no small action potential versus medium action potential versus large action potential. The action potential is either happening or not. It's not graded. All right. So let's talk a little bit more about the all or none law. And I want you to think about this in terms of the cutoff score for passing a class. Let's say the grading is pass-fail, and if you get to 70% on a test or a quiz, you pass. If you don't get to 70%, you fail, okay? It's a similar phenomenon with an action potential. If you get to -55, you have an action potential. If you don't, you do not have an action potential. If you score 71 on that exam, you passed. If you scored 100 on that exam, you still passed. There's no graded difference between what type of pass. Alrighty? So the size of the stimulus will not affect the size of the action potential. It will always reach positive 30 millivolts. You will not have a bigger action potential or a weaker action potential or any of that graded variation. Okay, this is very important. And this is how we differentiate an action potential from a graded potential. A graded potential can be small, it can be big, it can be positive, it can be negative. An action potential is one standard time, duration, amplitude, and it is not, there's no ability to sum or to add this. Okay, so this image pretty much highlights that concept. Okay, here we're comparing the membrane potential fluctuation with the type of stimulus. So we have three types of stimuli: subthreshold stimuli, a threshold stimulus, and then a suprathreshold stimulus. And as we can see, as long as we get to threshold in these two stimuli, the action potential looks no different. Okay, the time is going to be the same, the duration is going to be the same, the amplitude is going to be the same. We're only going to get to positive 30 millivolts. Alternatively, if we did not get to threshold, if we have a sub-threshold stimulus, we just have these changes in membrane potential, but we do not have an action potential. Okay, any questions on that? All right, there's a video that summarizes the generation of an action potential. I've posted it in the folder on Blackboard. So please, if you have time or when you make time, look at that video to get a good overview of the events that we've been speaking about. This image is really nice at tying everything together. And we're gonna go through this image sort of step by step, but it's very good. If you understand what's happening in this image, in this diagram, you pretty much understand what we've been speaking about. So let's go through this. I urge you to try to draw this or try to recreate this on your own. Okay, so we start out with a threshold stimulus, okay, which again could be several graded potentials that are added together and they meet the requirement for threshold. So they get to negative 55 millivolts. The next thing we have is the opening of those voltage gated sodium channels. We mentioned earlier that at negative 55 millivolts, those voltage gated sodium channels open, right? Both the activation and the inactivation gate, and sodium rushes into the membrane, into the cell. The sodium channels are open. Now this depolarizing of the membrane further potentiates more sodium channels to open. Okay, this is a part of that positive feedback that we were speaking about. So more membrane, more change of the membrane potential potentiates more opening of sodium channels. And that pretty much increases the membrane's permeability to sodium, and more sodium is moving across. Question? So the positive feedback loop here is that we depolarize the membrane, we got to threshold, we opened up a few sodium channels, we depolarize the membrane. The further depolarizing of the membrane opens up more sodium channels, which brings more sodium in, which even further depolarizes the membrane. So this is a positive feedback loop in that we're continually moving away from our set point, away from that negative 70, which is our resting membrane potential. Correct, correct. That is correct. Okay. So what we have is a net positive charge in the cell, rapidly increasing, and this is our upstroke or depolarization. This is the first part of the action potential. And again, this is positively feeding back onto this change in the membrane potential. So the more we depolarize the membrane, the more we open sodium channels, and so on and so forth. The second thing we do, and again, there's this delayed effect, but depolarization, or the depolarizing of the membrane, is the stimulus for the inactivation gates to close, but it's a delayed stimulus. So changing the membrane potential, anything above negative 55, not only depolarizes the membrane, but it sets up this delayed effect to then close that inactivation gate after 1 millisecond. Okay. Sodium channel inactivation gates will then close, and this will start repolarizing the membrane along with the opening here of potassium channels. So the delayed effect is the closing of the inactivation gates on sodium channels and the opening of potassium channels. Both of these effects, both of these activities are going to stop the membrane from further depolarizing at this point and start repolarizing. Okay, start the repolarization. So the membrane permeability to potassium then increases, and it decreases for sodium. And the membrane potential starts dropping back to negatives, back to towards the equilibrium potential of potassium, which is negative 94. Okay. There's rapid outflow of potassium from the cell. Potassium is being rushed out of the cell now until it gets all the way down. We said it's going to go lower than resting. It's going to go to about negative 84 millivolts. And then with the help of the sodium potassium pump and the leak channels, it's going to bump right back up to your resting membrane potential. Right? And this is a part of the negative feedback loop here. So when the cell repolarizes, becomes more negative on the inside again, this is going to turn off that initial stimulus here, like that initial depolarizing stimulus. So we have positive feedback for the voltage-gated sodium channels and negative feedback for the voltage-gated potassium channels. Any questions about this flow chart? Okay, very important. All right, so there are a couple of tables that I put in here to help you summarize, review, bring all of this information together. This one compares the stages of the action potential with the characteristics of the neuron at rest. Okay, so we're comparing what the voltage looks like through each of the phases, what gates are opened through each of the phases, what ions are moving, and so on and so forth. So again, I urge you to print or recreate this table blank and try to fill it in from your understanding of each of the phases and what's happening. Okay, and this second table compares the graded potential with the action potential. Okay, sort of what we've been speaking about. So for example, you can have summation with graded potentials, but you cannot with action potentials. All right, you have the time difference between graded potentials and action potentials. You have the direction of change from the membrane potential. So a graded potential can be depolarizing or hyperpolarizing, whereas an action potential is always depolarizing. We're always making the cell more positive at first.